a Portland Community College mathematics telecourse. A course in arithmetic review, produced at Portland Community College. Let's first come to grips with a basic unit called volume. A not exact but perhaps helpful word is the word solid. If I had a little cubic solid, 1 foot by 1 foot by 1 foot, we would call that hunk of solid a cubic foot, and it would be written 1 foot with an exponent of 3, which we will call cubic foot. Or for whatever the other kinds of measures we might have for measuring the edges of that cube. If the edges were 1 meter each, we would call it 1 cubic meter. Now, of course, this doesn't have to be solid. We could have a container with liquid in it, and this is our way of measuring the volume of that liquid. Also, we measure volumes in quarts and liters and gallons and cups too, but we'll work that in later. Now we want the volume defined by outside measurements of its container. Let's say that we have a larger, in this case a rectangular solid like a shoebox. To ask its volume is to say how many of those basic unit volumes, cubic feet, are in there. So like with square feet, if possible, we could actually count how many of cubes are there in this huge solid. And of course that's rather difficult. But we could use multiplication and realize if I took 4 times 3, I'm saying there are 12 in one of these ends. Then I have 5 of those stacks of 12. So there's 12 in this stack, 12 in this next stack, 12 in this next stack, and so on. So we would take 5 times the 12. Now, stating that mathematically, we would say this. The volume of a rectangular cylinder is simply the length times the width times the height. In our case, the length was 5, and the width was 4, and the height was 3. So back to our formula. The length 5 feet, width 4 feet, height 3 feet. Measuring the number parts, 5 times 4 is 20, times 3 is 60. And using this tick mark notation for feet is not quite so obvious, but it is true that you have foot cubed. So we say the volume of that rectangular solid is 60 cubic feet. So with what we've learned in the last few lessons, we know if we want the volume of a strangely shaped figure, rather than counting little cubes, immediately we'll go looking for some volume formulas. Say you were faced with a problem like this. What is the volume of a right circular cylinder if its base radius is 7 meters and its height is 25 meters? Now, involved in this problem probably are 2 or 3 questions. First, we might ask, what is a right circular cylinder? And if we were to look it up in a dictionary, we would find that basically it's an oatmeal box shape or silo shape. The right tells me that the sides are at right angles to the bases. Circular tells me that the base is a circle. In this 3-dimensional sketch it looks oval. So we have a right circular cylinder. And of course we now know what the base is. That's the top or the bottom, like the lid to the oatmeal box. Now that we know what it is, we can look in a handbook and find the formula for what we want, its volume. And we would find a statement like this. Volume is pi times the square of the radius times the height, where the height is the side of this box, and the radius, of course, is just that. And the radius of the top would be the same in this case. So now to work our problem, we would simply copy our formula over, substitute in the specific number values for these generalized variables, and we get pi, and the radius squared times the height. Now simply do the calculation usually on a calculator, remembering you do the exponents first. Notice I'm going to square a meter times another meter. So there's 2 meters times a third meter, so I'll have 3 meters being multiplied together, and that tells me my volume is going to be in cubic meters. That gives me sort of a check. Now squaring the 7 gives me 49 times that gives me 3,848.5 cubic meters. That's quite large. And they didn't tell us where we wanted to round off, so we'd be alert for that as we begin to use this result. Another problem: what is the volume of a sphere, ball shape, with a radius of 7.5 inches, accurate to the nearest tenth of a cubic inch? Now, by now we know enough to go running for a formula book, look up the formula for the volume of a sphere in terms of the radius. In doing so, we would get the formula: volume is 4/3 times pi times radius cubed. Now remember what this exponent means? Take 3 of those and multiply them together. So in our particular problem, we would have volume is 4/3 times pi times the radius, and the radius was 7.5 inches. See, 3 radii. Now we can see inch times inch times inch is indeed going to give me cubic inches, and the rest of this we do on the calculator. Now on my calculator, I'll take 4 times that times that times that times that, all divided by 3, or if you wish, 4 divided by 3, that times that times that answer times that product times that. In any case, we would get the same result, which would be this, and the text wanted us to round it to the nearest tenth of a cubic inch. This is 5 or more, so I drop it and round this up, so I have my volume to the nearest cubic inch. Now actually, if you had a scientific calculator with all these extra keys, you not only have pi on the calculator, which I do there, but you also have keys that will help you to exponentiate these numbers faster than actually multiplying them out. But never forget what this means. Take 3 of those and multiply together, including the units of measure. Another problem. By now, the technique of solution is rather routine. First, you identify the solid by name, the cone, and what its measure, its computation, apparently depends upon, and that's a radius and a height. Then in a handbook or somewhere, you look up a formula relating the volume to those 2 measurements. And here we have it. Do you sort of recognize that this bit here is the same as the volume of a right circular cylinder? We're just taking 1/3 of it, which tells me if I were to draw a cylinder that contains this, the cone that's in the cylinder is 1/3 the volume of the cylinder too. Now as you become better in mathematics, you'll always be alert for those kinds of relationships. Well, in our specific problem, of course we have pi. Our radius was given to us as 3 centimeters and the height is 12. So the radius is 3 centimeters squared and the height is 12 centimeters. Now squaring the centimeter, I'll have 2 centimeters being multiplied and 1 more centimeters, which is cubic centimeters. Now doing the exponents first. 3 squared is 9. 9 times 1/3 is 3. 3 times 12 is 36 times this. So you can see you can do much of it mentally. So 36 times pi is 113.097 cubic centimeters, but the problem asks us to round to the nearest tenth, so it would be 113.1 cubic centimeters. Now you probably, particularly on TV doctors programs, instead of hearing the word cubic centimeters, have probably just heard the phrase cc's, cubic centimeter. Sometimes it's written that way. This is the more appropriate way. Centimeters cubed. Another problem. What is the volume of a pyramid whose base is 70 feet by 30 feet, a rectangle, and whose height is 40 feet? You want it accurate to the nearest whole cubic foot. Now, of course, our problem is to find the key words, and that's pyramid. Looking that up in a math handbook, we would find this. Okay, the volume is 1/3 a capital B. Now in this case, a B is not a length, it's a base area, as they tell us here, times the height to the top of the pyramid. Well, in our particular case, our base is a rectangle, as is this, and it has the dimensions 30 by 70 feet, so the base area is the length, 30 feet, times the width rather, times the length, which is 70 feet. Multiplying those, we get 2,100 square feet. So this says the volume is 1/3 the base area, which is 2,100 square feet, times the height, which the problem gave us as 40 feet. So again, slide this over a bit. Again, we have feet times 2 other feet being multiplied, which is cubic feet. 1/3 of 2,100 is 700. Now this is easy enough. We can multiply mentally and get that that pyramid would have 28,000 cubic feet to it. Now, by all means, this doesn't even touch the availability of solid formulas, volume formulas. But at least you have the strategy. Identify what you're talking about, look up the formula, identify the parts of the formula, substitute in the given information, compute by following the laws of order of operation and the laws of measurement numbers. And that's all there is to it. And of course, when it gets messy, we use calculators. As was the case with areas, in real application problems, when you need volumes of solids, quite frequently it isn't a simple solid, it's a composite solid. So again, like with area, you try to decompose this solid, in this case a grain storage bin or a silo, into component parts. Now if we were to take this part here, indicated by the blue on our sketch, that is clearly a cylinder. So at least we could find the volume of the lower portion and then later find the volume of the upper cap and add that in. So recognizing that this lower portion, the blue portion, is a cylinder, we know that our task is to find a formula for that if we don't have it memorized already. So having found the formula, we simply replace the variables by their indicated amount. So pi 3.1416, radius, well, they gave us the radius was 10 feet, so we might as well square that right while we're here. So 10 times 10 is 100 square feet. Then the height was indicated to us as 40 feet. And of course, 2 feet being multiplied times the third foot is cubic feet. So multiplying 100 times 40 times pi, we would simply get 12,566 cubic feet rounded to the nearest whole cubic foot. So we now have the volume in cubic feet of the cylinder part of this silo. So looking at what's left, do you recognize what that is? It's as though you'd taken a ball, a basketball, and cut it in half. So what we have here is a semisphere, or if you will, a half sphere. Well, we know that the volume of a sphere is 4/3 pi radius cubed, and semi means 1/2 of that. So we now have a formula for the volume of a semisphere, even though it wasn't given to us in the handbook, but this was. And knowing what a semisphere means allows us to derive, if you would, the formula for the semisphere. And of course, you might notice here is an obvious cancellation that I might as well do. So I have 2/3 times pi times the radius of this semisphere. But the radius is the distance from the center to the outer edge, which is either there or here. They're all the same because the sphere has the same radius everywhere. Well, this one right here we know down here because this is the same circle here as we have here. So the radius is in fact given to us as 10 feet. But we can cube it mentally. 10 times 10 is 100 times another 10, see here's cube, is 1,000, and that's in feet, so the volume will be in cubic feet. So all that remains is 2 times pi divided by 3 times 1,000 cubic feet. And of course, with that much arithmetic, usually is done on the calculator. So doing it, we have our volume to the nearest whole cubic foot, which is the volume now of this semisphere top of the silo. Putting that together with the volume of my lower portion, the cylinder, adding those two, we would get the total volume of the whole structure, which would be 14,660 cubic feet. But let's say, for whatever the reason, somebody would like to know how many cubic yards is that. This means in a conversion handbook we must find a relationship between cubic feet and cubic yards, or else we must somehow derive that relationship ourselves. Let's derive it from ground zero, just to indicate that you don't always have to look things up. Just common sense, math, along with what you do know, will usually allow you to deduce what it is you want to know without actually looking it up all the time. So we're going to involve ourselves momentarily in a deduction. That's a good word for you. Simply means start with what you know is true and do to it that which you know is legal and permissible, and get to what you want to know. That is a relationship between cubic feet and cubic yards. Well, let's start with the larger of these two, the yard, and ask what do we mean by cubic yard geometrically? Well, it's simply a cube that is 1 yard deep, 1 yard wide, and 1 yard long, and out of that you construct your cube that is 1 yard on an end. Now we want to relate that to cubic feet, but we know that 1 yard is 3 feet, and of course all the way around. Do you get a feel for what we're about to do? Because the volume is length times width times height of a rectangular solid. So in yards, 1 times 1 times 1 is still 1. Yard times yard times yard is cubic yard. But let's determine the same solid in terms of feet. Since it is a same solid, we're allowed to say equal. So now we have 3 times 3 times 3, length times width times height, which is 27, and feet times feet times feet is cubic feet. Again, see how it's a units as directing our attention. The numbers is simply what follows along. This is the reverse of perhaps what you remember from grade school, high school, where you concentrated on numbers and sort of tacked this on as an afterthought. But in fact, in higher math and science, it's the units that direct our attention and our work, and the numbers parts just sort of follow along. But with this kind of reasoning now, we have a bona fide relationship between cubic yards and cubic feet. And using that, we just go through a standard conversion of units, which we've done so much. Let me just do it rather rapidly. 14,660 cubic feet, written as a fraction. I want a cubic foot on the bottom to cancel that. Here's my relationship with cubic feet. 27 of them is equal to 1 cubic yard. That cancels with this. I end with what I wanted to end. My arithmetic statement says to divide this, here's my division, by 27. So dividing this by 27, I get 543 cubic yards is the same volume as 14,660 cubic feet. But now, just for some variety to this, someone might just as well have said, what is this volume not in cubic feet, not in cubic yards, but in gallons? Well, that means I can convert this to gallons if I have a relationship between cubic feet and gallons. Or I can convert this into gallons if I can find a relationship between cubic yards and gallons. So I checked with a handbook, textbook, and in my case, the back of a collegiate dictionary, and it was found that 7.48 gallons is 1 cubic foot. Dry measure, by the way. If you use liquid measures, this will be somewhat different. And many handbooks will give simply 7.5. They will round this off, which means you're using a highly approximated number. But again, our conversion in units now says I can go from gallons to cubic feet or cubic feet to gallons. Well, here's my cubic feet. 14,660 cubic feet. My conversion of units principle tells me I need cubic feet on the bottom so that I can cancel. Here's my cubic foot bit. I need an equal amount on top, so that's 7.48 gallons. Indeed, my cubic feet cancels. I do end in gallons, which is what I want. So now my arithmetic indicates I take this arithmetic part times this arithmetic part times the gallon. So doing that, I would get about 109,000 gallons. However, note this. This was only approximated to 3 digits of accuracy. So even though this one has more digits of accuracy, my final answer is really no more reliable than my least reliable single multiplier. So that means that this answer really is not reliable except for the first 3 digits. So counting out the first 3 digits, which is the 9, and the one before it is 5 or more, so I'll round this up, give me 110. But I have to keep my next 3 0 placeholders to keep the magnitude right. So we say that's approximately 110,000 gallons. Do you see how in the end everything comes into play? Our use of formulas, our order of operations, our concept of volume, our conversion of units, and our knowledge of round-off. All must be brought to bear just to adequately solve this one single problem. And since we have but a few moments left, rather than working another problem, let me give you some generalized volume formulas that are not in your textbook that you might wish to note down and keep handy with you for the future. Let's give ourselves a class of solids in which the two bases, the bottom and the top, are exactly the same shape. And furthermore, that we either know or can compute the area of that base, and we also know the height between the two bases measured along a perpendicular, even though our solid itself might be slanted as it is here. Nevertheless, there is a distance measured on the vertical between those two bases which have been slanted off from each other. Many textbooks will name such a generalized concept as this as a prism. You must be careful because some books will use this word in a little bit more restrictive of sense. But the volume of all such defined figures is the area of the base times the height between the two bases. Now, do you see that our cylinder was a special case of this? That the pi r squared of the cylinder formula is really nothing more than the area of the base, which is the same as the top, and the height is the distance between those two as measured on a perpendicular. So this is merely a special case of a larger category of figures. And if we have an area going up to a point with the distance from that point dropped perpendicular to the base, the generalized volume formula is 1/3 the area of the base times the height. Now, do you see that the cone is a special case of that? Here's my 1/3, and pi r squared is nothing more than the area of the circular base, and here's my height. So any figure that fits this condition will have this as its generalized volume if you understand the capital B to be the base area. Do you see that the pyramid as well fits into that category? That's 1/3 the area of the base times the height between them. This would also work if this had been slanted rather than being symmetrical as it is here. You might want to look these generalized formulas up in a math handbook if you use formulas a lot, because by generalizing formulas, you will have fewer to remember. This is your host, Bob Fennell.